When an LLM emits invalid SQL, prompting it again repeats the mistake. Parse the failure with SQLGlot, repair the AST, and verify the query safely in DuckDB. You'll build a SQL AST repair loop that fixes invalid text-to-SQL queries and executes only verified select statements. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Text-to-SQL can feel magical until it breaks. Models often emit SQL that looks right but won't run. Left unchecked, that crashes pipelines, bubbles errors to users, or triggers risky retries against live data. We need a predictable pattern. Detect bad SQL, make narrow edits, and only execute what we verified. That's the practical goal of AST repair for invalid text-to-SQL. The core move is straightforward. Parse raw SQL into a tree, apply small auditable edits to that tree, and re-emit only after a quick safety check. That keeps execution separate from model hallucination and gives you measurable signals, counts of repairs, skips, and successful runs. We'll build a compact loop showing 3 repair modes: parse error detection, dialect normalization, and controlled schema fixes. Then gate execution so only verified selects run. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we start by capturing parse failures and turning them into structured signals before trying any fix or execution. This snippet catches the first hard boundary. Invalid SQL should become a structured failure, not a database incident. SQLGlot's parse1 call tries to parse raw SQL using the DuckDB dialect, and parse error gives the repair loop a deterministic branch when syntax is broken. That matters because blindly retrying the same prompt can repeat the same typo and burn latency without improving safety. The code does not repair anything yet. It only separates parsable text from text that needs repair or rejection. The visible output shows the failure class, which becomes the first signal for routing the query. We saw parse failures. Next, we try a cheap, deterministic repair that often fixes only syntax differences between dialects. This example fixes a dialect mismatch before it reaches execution. The incoming raw SQL uses T-SQL's top syntax, but the local engine is DuckDB. So, parse1 reads the source dialect, and tree.sql emits DuckDB SQL. This is a cheap repair path because the SQLGlot AST preserves the query intent while changing the emitted surface syntax. In an LLM app, that gives you a deterministic alternative to asking the model to remember every target dialect rule. The visible output shows a DuckDB-compatible query, which proves the repair change syntax without executing anything. Dialect fixes help, but schema errors still slip through. Now we walk the AST to correct column names with a controlled rule set. This code repairs a schema mistake at the AST node level instead of editing SQL text blindly. The scores dictionary represents a tiny deterministic selector, where amount beats region for the misspelled total column. Repair columns walks SQLGlot XP column nodes with findAll, replaces only the bad column, and then regenerates fixed SQL for DuckDB. In production, the scoring source might come from catalog metadata, embeddings, or logged correction rules, but the boundary is the same. Only known selected replacements enter the tree. The visible output shows the corrected projection, which matters because the repair is narrow and auditable. Repairs look okay now, but we must never execute arbitrary ASTs. Add a strict execution gate and run only what passes. This snippet adds the execution boundary engineers usually want before connecting LLM output to data. DuckDB is created in memory, loaded with two simple orders, and isSafe allows only a SQLGlot X select tree through. The repaired fixed SQL is executed with db.execute only after that AST check passes, and fetchall returns the concrete result. The guard is intentionally small for the tutorial, but it shows where stricter policies fit, such as table allow lists, row limits, or blocked functions. The visible output shows rows returned only after verification, which keeps repair separate from execution approval. With parsing, dialect normalization, column fixes, and an execution gate working in isolation, we now drive them with a small loop that treats LLM outputs as inputs and records results. This example ties the repair loop together with a small batch of LLM-like outputs. The first query gets a deterministic syntax normalization. The second goes through repair columns for the misspelled column. And the third is parsed but rejected by isSafe before DuckDB sees it. Parse error still has its own branch, so unfixable syntax can be skipped without falling into database execution. This is the baseline shape to monitor in production, count repairs, skips, and executions as separate outcomes. The visible output shows 2 verified executions and 1 skip, which proves the loop can repair useful SQL while blocking unsafe SQL. In a real project, you would map these outcomes to metrics. Log 1 counter for parse failures, 1 for AST repairs, and 1 for rejected executions. Those numbers tell you if the model needs better prompts, a richer schema source, or stricter safety rules. What this is: a small loop that parses LLM SQL, applies narrow AST edits, and only runs checked select queries. When to use it: whenever you run model-generated SQL against real data and need predictable safety and auditability. One caveat: the repair rules must be conservative. Over-eager fixes can change intent. As a concrete next step, add a table allow list and a row limit check-in isSafe, and tune the row limit from 10 to 100 to see how it affects useful results versus risk. That single parameter will show whether your guard is blocking useful analysis or protecting data appropriately. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.